lot of attention lately on the tiny additives in our shower products. It seems, without many of us realising, they've been stuffed full of plastics.
They're designed to make things a little bit rougher and to get a better clean, but a lot of the products that they're used in go straight down the sink and then out into our lakes and rivers and oceans.
Called microbeads, these tiny plastics have been causing so much alarm that supermarkets are in the process of banning the bead from their shelves. But in the stomachs of our seafood, researchers are mostly finding a different kind of microplastic.
Major thing that we were finding were these fibres, and so that really begged the question, where do they come from?
They're going down our household drains at an astonishing rate, but barely anyone seems to realise.
If animals that we're eating are eating plastic, we could potentially make that assumption that these chemicals are in our seafood.
What kind of microplastics are ending up in our marine life, and how much damage can they actually do? When I decided to take a closer look at microbeads, I didn't realise just how close I was going to have to look. They're so small, aren't they, these tiny little beads?
Oh, they're tiny. We're getting sizes right the way from 1 millimetre all the way down to several micrometres, if not smaller.
The man helping me filter these rinse-off cosmetics is ecologist Dr. Mark Brown. He's been consumed with the problem of microplastics in the oceans for more than a decade.
It is a huge problem. So if you look at the amount of plastic in the environment, over 85% of that is microplastic.
The problem with microbeads is they're so small you need a filter paper to catch them. They're too small for our water treatment systems, but small enough to be easily ingested.
Over recent years, the amount of research has increased, and we've started to show that they're persistent, bioaccumulative and toxic.
3 years ago in the US, scientists trawling for microplastics in the Great Lakes found concentrations as high as 400,000 particles per square kilometre. They were amazed by how many tiny spherical beads they found in the mix.
It isn't just microbeads, it's much larger bits of plastic breaking down into the same micrometre-sized fragments. And so we're really concerned as to whether or not these particles could be accumulating in humans and wildlife.
The evidence shows they are, even at the very base of the food chain. Zooplankton, for example, are a major source of food for fish, whales and seabirds. These were filmed under a microscope in just one drop of water. Normally, they draw algae towards their mouth by creating currents with their legs, but when tiny fluorescent particles of polystyrene are added to the water, they eat those instead. Microplastic is now regularly being found in wild-caught zooplankton in the North Pacific. Just through eating these tiny crustaceans, salmon are thought to be consuming around 90 particles of plastic a day. So these particles look so small that if you swallowed them, it doesn't look like they'd do much harm. I mean, don't they just sort of pass right out the other side?
Well, this is what we thought until we started doing experiments whereby we were actually feeding these types of particles to them. We were astounded by actually what we found.
I'm much more disturbed by what Mark shows me next.
So we know that invertebrates, in particular mussels, are exposed to microplastics in the environment. What we really wanted to find out is whether or not these tiny particles of plastic get any further than the stomach itself. So we exposed these mussels to tiny particles of polystyrene, and we then tracked these particles in the tissues of the mussel itself.
This footage, captured by marine scientists at the University of Connecticut, shows how tiny bits of plastic are drawn into the mussel and along the gill filaments. They get trapped here just like food particles and pass down the ventral groove into the mussel's mouth. But no one knew they could penetrate the gut barrier until Mark took samples of the mussel's blood. When the blood is analysed days later under a special infrared microscope, the molecular vibrations of plastic can clearly be identified.
Here you see right in the middle of the actual slide there is the polystyrene bead.
So that means that the plastic has made it from the stomach of the mussel into the circulation?
It has, yes.
That's astonishing. So how long have you seen the particle remain in the circulation?
They've lasted in the actual muscle for 4 months. But more disturbingly, as these particles of plastic get smaller, which is what they're likely to do through the breakdown in the environment, the rates of transfer actually increase massively. The concerns that we have really is that it can cause inflammatory responses, so the body of the muscle itself recognises it as a foreign particle and starts attacking that. Because the particle can't go anywhere, you get scar tissue forming around that.
But the reaction to a foreign body in the tissues is just one of the side effects. What's most concerning researchers is not just the physical damage caused by microplastics when they're ingested, it's the toxic load from the chemicals they carry. One of those researchers is Dr. Chelsea Rockman from the University of California.
I'm an ecotoxicologist, so I look at the fate and effect of chemicals and plastic debris in our environment. Plastic is kind of like a little sponge for a lot of the chemicals that are already out there, the pesticides, the flame retardants, industrial chemicals, etc. Plastic concentrates, hyperconcentrates these chemicals at very large concentrations, sometimes 1 million times what we find in the water column. So PCBs, which were banned in the early 80s, DDT, which was banned in the early 70s. And I find these on every single piece of plastic I take out of the ocean. Metals like copper, lead, nickel, cadmium.
Plastic also contains unique chemical additives of its own from the manufacturing process, such as flame retardants and antimicrobials.
So the big question there was, do these chemicals associated with plastic debris end up in animals when they eat them? So basically we set up a study in the lab where we fed fish plastic that had these chemicals associated with them. We fed them environmentally relevant levels.
Dr. Rockman exposed Japanese Medaka to plastic particles that had been pre-soaked for 3 months in San Diego Bay. After just 2 months, higher levels of what's known as PBTs, or persistent bioaccumulative and toxic chemicals, were measured in the flesh of the fish, particularly flame retardants unique to the plastic.
So a lot of these chemicals are fat-loving and water-hating. But once they've transferred from the water into that fat phase, so the fat in a fish, they're incredibly persistent. I might have, a mechanism in my liver to take that PCB and break it down into a safer form. But once my liver is overtaxed, it might have a hard time doing that, and I'm going to start storing those chemicals in my body.
Chelsea predicted signs of damage would first be seen in the liver. Here she observed cell death and excess fat, a sign of liver overload. One fish even developed a liver tumour.
And when we've taken fish in the lab and fed them the virgin plastic that doesn't have this mixture of things from the environment, we see less of an effect in the fish. So this mixture is having an effect.
Even at very low concentrations, flame retardants are known to cause endocrine disruption, an effect observed in the fish.
So endocrine disruption is a disruption in the hormone system, which is what controls reproduction. So if that's not functioning, some people joke, if you don't reproduce, what are you here for? So it's a very important system.
Dr. Mark Brown also found chemicals transferred from the plastics to lugworms, a common marine sediment dweller.
We saw reductions in survival, reductions in immune function, and we saw a reduction in their ability to feed and process sediment. Things like triclosan, which is sort of an antimicrobial, is added to plastics, and that was one of the major killers of the worms.
Worms that process sediment are crucial for the survival of a complex food web of organisms.
And so when you remove these worms from the environment, you see a complete reduction in the numbers of animals and plants that can actually live on that shoreline.
These studies raise the important question: if chemicals can transfer from plastic to marine life, how much of our seafood is eating plastic?
I got it. It's huge though. Well, maybe it's huge. Let's see.
Here in Sydney Harbour, we're out catching some of the state's most popular eating fish. Or at least trying to.
This is called a tiddler. That's not what you're after, is it?
We've looked right the way throughout Sydney Harbour, which is a really big harbour, and we found a surprisingly high concentration of microplastics in the sediments, and up to 60 per 100 mils of sediment. That's a really high concentration.
So is that why you think you'll find plastic in the fish?
Yeah, so because we did find high concentrations in the sediments, the first thing we wanted to do was to see which species it was getting into, if any, and so we targeted the fish that were feeding on the sediment. And this is a mullet. This is really a target fish for us, and these guts in here are full of sediments.
So this is a popular eating fish?
It is popular. It's not quite as tasty as the bream. It depends on your taste. These bream are really tasty, so these are really targeted by the recreational fishers.
We're taking these fish back to the Sydney Institute of Marine Science, where researcher Jen Halstead has been looking through their guts for any traces of plastic. Her studies have revealed that 30% of the mullet and 13% of the bream have plastic in their guts. But typically, it's not coming from face scrubs or shower gels.
So I've just found something that looks suspiciously like a plastic. Do you want to take a look?
Yep. Doesn't really look like a microbead at all.
Yeah, well actually most of the microplastics that we're finding are in these forms of fibres, so that looks a lot like what we've been finding.
So is that a plastic fibre?
Yeah, well we actually don't know at this stage. It could be synthetic, it could be natural. That's why we need to take under further investigation.
These results mirror a study 2 years ago by Dr. Chelsea Rockman, who looked inside the guts of fish from both Indonesia and the US.
I'm collecting fish from local fishermen that are selling them for human consumption, either out of a local market, straight off the dock, as you see here, or it's actually going through Pillar Point Fisheries over here, which then gets shipped.
Back in the lab, Chelsea discovered around a quarter of the fish from each country had debris in their guts. But the type of plastic differed.
So what you see back here is a really good example of a piece of plastic taken from a fish in Indonesia. So this is from a silverside, which is a planktivorous fish, actually about this big. And what's a little bit disturbing about this one, actually, is that people eat the entire fish. And this is an example of where this plastic actually would go to, be transferred to a human.
In Indonesian fish, all of the debris was microplastics from larger, broken down pieces. But in the US, Chelsea mostly found microfibres.
But if you look closely at this, you can see like the actual, nylon intertwine. That does not look natural, plant-like.
Chelsea didn't pinpoint the source of the fibres, but with the help of vibrational spectroscopists at Sydney University, Dr. Mark Brown has followed the trail further.
The forensic techniques that we use shine an infrared beam or laser onto the sample. And we use that absorbance and reflection of light to tell us the type of polymer that we're actually finding there.
The vibrational fingerprints of fibres found in Sydney fish do indeed match plastic, but from a source that to me was totally surprising.
When we match this to a database of polymers, it clearly identifies this one as nylon. The second one here matches to polyester, polymers used in clothing. They seem to have a high fibre diet and it's full of synthetic fibres. They certainly seem to be the same types of fibres, same physical structure, the same colours.
Well, with the mullet, we caught 30% of them had a microplastic particle, at least one, in their gut at the time that they were caught. If you model that, it actually means that pretty much every mullet is eating at least one microplastic particle every 3 or 4 days.
I'm amazed, but Mark has suspected it all along. He's looked at multiple shorelines on 6 different continents, and in each case, fibres were the dominant microplastic.
We expected to find lots of small particles from either from the facial cleansers or from, larger bits of plastic that had broken down. But the major thing that we were finding were these fibres. What was peculiar about what we were actually finding was the proportions actually matched the types of polymers used in the textile industry, not only in terms of the types of fibres, but also in the numbers.
The closer they were to sewage outfalls, the higher the concentration of fibres.
And we found exactly the same types of fibres, acrylic, nylon, polyester, being emitted from these sewage treatment works.
The simple answer seemed to be that fibres were escaping from washing machines.
So most of the fibres that we're finding in the environment were polyester, so we essentially chose some garments that are made out of polyester, things like fleeces, which are the poster child for sustainability because a lot of bottles get recycled into them. And we essentially put those into washing machines separately, and we counted the number of fibres that were coming off.
You probably haven't thought that much about the proportion of clothes we wear that are plastic. But today, around 2/3 of the clothes we buy are made of synthetic fibres. The so-called eco-fleece sheds almost 2,000 plastic fibres each wash. Other polyester garments aren't much better.
They release similar quantities into the environment. It doesn't seem just to be one type of garment, they all seem to be doing it.
But can these thin fibres carry the same chemical load as the other more spherical plastics tested?
I think the toxicity of the microplastic particles will vary with their shape and size. So the fibres have an incredible amount of surface area. The more surface area, the more likely they are to actually carry those other contaminants, and they would then be transferring into the fish tissue.
Aside from the direct effects of eating plastic, chemical doses are already known to biomagnify up the food chain.
These chemicals might absorb to the plankton at the bottom of the food chain, and one fish eats 10 of those plankton. Now that fish has a larger dose, right? 10 times the dose of the plankton. And then several of those are eaten by a larger fish. And so the question is, how is plastic contributing to this thing where we're seeing these large concentrations of chemicals in top predators?
One of those top predators is us. And it's well established that toxic chemicals can transfer from contaminated fish to humans with serious side effects. With all the billions of people wearing plastic clothes, suddenly the problem appears a lot more diabolical than microbeads.
We've been speaking to the public, government and industry. The public have voted this one of the most important issues to be sort of tackling. We've spoken to the government about it. Yet they seem to be focusing on other activities, things like microbeads and also packaging. When we have gone to talk to clothing companies or appliance manufacturers for washing machines, the appliance industry and the clothing industry haven't been helpful.
Mark says a simple filter could be added to washing machines to stop all kinds of toxic fibres from reaching our seafood. And do we really need all the industrial chemicals added to our clothes and other plastics?
We're seeing all sorts of chemicals come on the market, up to about 15,000 per day. The problem is that we're not doing the tests to keep up with the types of impacts that could be occurring. Which one's causing the impact and which one's is causing more of a worse impact? If we understand that, we can start making choices.
We need a healthy ocean because it is all connected, and our fate